Hello everyone, welcome to my channel Euclid Mathematics and welcome you all here on my next lecture on coset chapter. Okay, so in my previous lecture I explained to you all coset and the left coset, so which you can check in my playlist. I added a left coset chapter and example depend on left coset in my playlist. You can see that one. If you have any doubt, difficulty, you can ask me in the comment section. In my today's video I will explain to you all coset but with a right coset. Okay, I explained one example with a left coset in my previous lecture. Now in my today's lecture I will explain coset with a right coset, which include one example. Okay, I'm going to explain one example here. So this topic is more important for the further topics that we are going to learn. So first of all we need to understand the definition of a coset. Okay, so you can see here right coset and left coset. If you want detailed understanding of a coset, you can check it into my previous playlist. Okay, so here left coset h into h and right coset h into h into a. Okay, and a belongs to group G and small h belongs to subgroup of h. Okay, so by using that definition, let's find out one example. Okay, that gives us the right coset for our group G. Okay, now let's go for the example. Here it is, our first example. Let's get started our example here. Group G I consider here as a Z integer. Okay, the value of integer it is I consider group G, and H subgroup. Okay, H I consider 3Z is a subgroup of a Z. Okay, and find all cosets of H in G. Okay, find all cosets of H in G. That means we want the cosets of our group G. Okay, so G is given this set. Okay, because we know that Z is infinite group. It is having infinite number of elements. So we cannot find all elements here because this is the infinite group. As we go for further operation, it will go bigger and bigger. We go for some selected few operations here. Okay, now I consider here G as a Z, 0 plus minus 1 plus minus 2, and subgroup. Okay, subgroup it is here 3Z. 3Z means multiple of a 3 into our group G. Okay, so 3Z is here 0 plus minus 3 plus minus 6 and so on. As we know the definition for left and right coset, we multiply A from our group G, H from our subgroup G, H. Okay, so H and G we need it here. Okay, by using G we need element A, and by using H we need element H. Okay, now let's take the one element from G. I taken here 0 and H it is here subgroup 3Z. So add that 0 to 3Z. So we get the 0 plus minus 3 plus minus 6. It remains same because 0 is identity element. When we add, it goes to identity itself, that group itself. So 0 plus 3Z it remains 3Z. So I selected first element 0 and then I added it to the subgroup plus 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 so on. Okay, so this one is goes to infinity. So second one, consider plus 1 from G and add it to the subgroup H. 1 plus 3Z. 1 plus 3Z it is here 1 plus 0 1, 1 plus 3 1 plus 0 1, 1 plus 3 4, 1 minus 3 minus 2. So add 1 here to all element, you get the next coset. Okay, next coset it is here. Similarly, select second element 2 from our G, add it into the subgroup, you will get the next coset. So 2 plus 3Z, so 2 plus 0 2, 2 plus 3 5, 2 minus 3 minus 1. Okay, so you can see that element goes to positive and negative here. So that's why I added here positive, here it is negative. Similarly, go for the 3 belongs to Z such that, okay, now you can see here 3 belongs to Z. So which contain the element that add it to the subgroup. So 3 into 3 plus that subgroup. So 3 plus 0 it remains 0, 3 plus 3 6, and here for negative sign also same. So 3 plus 3Z it comes 0 plus minus 3 plus minus 6 and so on. Okay, this is the addition for 3 plus 3Z. For similar leftover element, so how many elements remain here? You can see it here in our group G. There are infinite number of elements. You can take remaining element also. Okay, so like a 3 plus 3Z, minus 1 plus 3Z, 4 plus 3Z, 5 plus 3Z, and find out. And once you get all these cosets, just try to observe them. Which are equal? Those are equal, take it them and to one side, and another those are not equal. Okay, take it to the other side. That means all equal element gives their intersection. All equal element gives their intersection as our group intersection as a phi, and their union it gives our group G. It is the definition for left coset and right coset. Okay, as we see in previous lecture, the union for two coset of our group G, it is a group G, and intersection it goes to empty set as a phi. Here you can see here I got the similar value for 0 plus 3Z, 1 plus 3Z, 2 plus 3Z. Okay, so these are the value from our coset which are distinct coset of a 3Z in a Z. Okay, 3Z is the subgroup of a Z, such that if we select 0 plus 3z union 1 plus 3z union 2 plus 3z, we get the whole group Z. Okay, not only that one, because these are the coset that can generate a whole group, so we have to select only the coset which are same at here. Okay, so 0 plus 3z, there are similar element that gives the value for 0 plus 3z, similarly here and similarly here, and if we take their union, we get the group G. And if we take their intersection, 0 plus 3z 1 plus 3z, we get the empty set. This is the property for coset. Union of all cosets, it is a group G, and intersection of all coset, it goes to empty set. Okay, then 3z has a distinct coset. Okay, so this is the way to find out the cosets of our group. I hope so you all have understood my second lecture on coset, that the way to finding the left and right cosets. Okay, so if you have any doubt, difficulty, you can ask me in a comment section. I uploaded a similar video on my YouTube channel. Okay, you can check it into my playlist. So thank you everyone. Thank you for my today's lecture.